All right, good afternoon. My name is Jesus del Alamo. Let me take this off so you can hear me well. My name is Jesus del Alamo. I'm professor of electrical engineering. And I'm delighted to welcome you to the first seminar of a series that we'll be running every once in a while in concert with the MTL seminar series that is actually a joint seminar between MTL and the new MIT AI hardware program that we launched last spring. So this is a program that attempts to gather colleagues that are interested in various aspects of AI hardware to be able to contribute to this very important bottleneck towards the future of artificial intelligence going forward. The hardware has been a bottleneck to the development of AI algorithms, and it will continue to be so going forward. And we want to agglutinate colleagues that are working in that area and try to formulate research programs that can really make an impact. So this is the first one such seminar that will illustrate issues of AI hardware. And for this first seminar, we're delighted to have here Dr. Murat Onen from MIT to give our first seminar, which is titled Devices and Algorithms for Analog Deep Learning. So let me tell you about Murat. He has a bachelor's in electrical engineering from Middle East Technical University in Ankara in Turkey, and then a master's degree in ECS here at MIT, and a PhD in ECS that he finished this last year here at MIT. His master's was with Professor Carl Berggren on superconducting electronics. His PhD was in my group in this area that he's going to describe today. He was a research intern at IBM T.J. Whiteson Research Center for 2 summers in 2016 and 2019, and according to what they tell us, this was an extraordinarily productive set of experiences that produced 14 patents and first author patents and many other patents and many publications. So Murat has done really very exciting research that he's going to describe right now, not just on new devices for artificial intelligence, but also new algorithms to be able to exploit the uniqueness of these devices and to also work around some of the non-idealities that these devices have. And it is this really full stack type of innovation that is really going to be needed to push AI hardware forward and continue to realize the tremendous potential of artificial intelligence. Murat, thank you very much for leading us in this very first seminar. We're looking forward to your talk.
Thank you very much, Jesus, for the very kind introduction. Ladies and gentlemen, welcome to my talk. My name is Murat Onen, and today I'll be presenting you analog deep learning. Specifically, by the end of this talk, you will have seen why we urgently need better AI hardware, why and how can analog deliver that, and what are the necessary steps we need to take in order to get to that point. As for the overview of this talk, I will start giving with a relatively lengthy introduction, assuming no prior knowledge in the field. Then I will follow it up with some examples from my own research. I first want to start the talk by spending some minutes on what makes deep learning so special, why we are so interested in it. So when you have abundant labeled data, which we do today, and when you build connectionist network architectures, such as the one illustrated in the background, you can then train these systems to find representative features of a data set and form abstract relations between them. To exemplify what I mean by this, let's have a look at GPT-3, the state-of-the-art natural language processing model we have today. For those who are not familiar with GPT-3, you can think of it as a massively advanced Alexa or Siri, in the sense that it inputs queries in text form, and then it also outputs the answers in the text form, which is why they're often called as natural language processes. So if you were to ask GPT-3, why is bread so fluffy? It then returns the answer detailing the leavening process that goes into it. And what is so interesting about this compared to, say, finding the same answer through a search engine is that GPT-3 actually has never seen this information throughout its learning. What it is doing instead is that it is building this representation through many low-level associations. Associations that contains features that it learned throughout its training over a very large data set of examples. To put that into context, GPT-3 was trained across the entirety of Wikipedia, and that still comprised only 3% of the complete thing. So, as you might imagine, training this network has not been an easy task. Specifically, 10 to 23 floating point operations were necessary to train this network start to end. And note here that this is only the last training, so it doesn't involve the experiments that went into it to design the structure itself and optimize the parameters. No, this is the training that ended up being GPT-2, only the final one. And if you were to do this using a single high-end GPU, it would take 355 years to converge. Obviously, what researchers did instead was to harness enough compute power to manage this task in a matter of weeks at a data center, but that came at a heavy cost of $15 million. What we do know with almost certainty is that these numbers are only going to go increase from this point. By 2025, estimations suggest that training this state-of-the-art network is going to cost over $1 billion, and it's also going to consume higher power than the entire New York City. So what this means is that as we are moving towards advanced AI applications such as autonomous systems, intelligent decision aids, or natural language processes, fewer people will be able to afford such costs, and leading to monopolization of AI. And ultimately, whoever has the best hardware is going to take it all. That's exactly why you won't be surprised to see that there have been a plethora of attempts to realize advanced AI chips. Here I'm showing some of them plotted with respect to their in watts and peak performance in giga operations per second. So if you go up and right in this plot, what you are basically doing is you are giving more and more power to the system in order to get higher peak performance, which is why you start seeing data center level systems. Instead, if you move the opposite way towards the origin, you will start seeing edge compute systems where the resources you have are limited, so you can't allocate all that much, but you're still trying to get the most performance out of them. In order to be able to compare these two ends of the spectrum and everything that lies in between, researchers often use a normalized metric, which is operations per second per watts. And these are the lines that are shown as the dashed line crossing across this graph, as you can see there. The issue that we started seeing is that digital CMOS-based architectures started to seem to get limited by this 10 tops per watt line. And the problem with that is that amount of performance will simply not be enough to power the applications that I was just mentioning you about. So if you combine this with the diminishing returns we are starting to get from scaling benefits that has powered us for so long, the situation starts to look a bit dire. And that is exactly why analog hardware started to become of interest, as they promise performance metrics around 1 petaops per watt. That is 2 orders of magnitude higher than what we are getting limited by today. So in order to understand how this graph itself emerged, both for digital architectures and for analog architectures, let's have a look at what are these operations that we are trying to execute, why can't digital handle them in an efficient manner, and what makes analog ones so special that they can promise at least these kind of metrics. Bulk of deep learning comprises 2 key tasks: testing the inputs and updating the weights. So when you present the image of a cat to an image classification network and ask what this belongs to, what you end up doing is a series of matrix inner products between the input image you have and the successive layers of the weight matrix. And then when the network returns you the answer saying that this image belongs to that of a tree, you need to update the weights using a series of matrix outer products this time. And the issue is matrix inner products and outer products, or matrix algebra in general, is particularly tricky to be executed on conventional digital architectures. Well, first of all, whenever you want to do either one of these operations, you first need to bring these weight and input matrices from the memory to the processor. And then once the operation is done, you need to write them back to the memory. And at the very large scales of matrices that we're dealing with today, this quickly exhausts the memory bandwidth we have, causing the infamous von Neumann bottleneck. But it doesn't end there. Even when the matrices are finally in the processor, executing these operations have a high computational complexity of O(n) cubed, meaning that if you were to do the same operation with a matrix that is 10 times larger, you need to do 1,000 times as many operations. So if you have a serial processor, such as CPUs, it is also going to take 1,000 times the computation time that you will have. Of course, there is an alternative. You can divide this computational load into many parallel subloads by distributing it across. But the problem there is that each GPU core we have, such that you can divide this into the parallel loads, they comprise of several hundreds of transistors. And at the amount of which that we need to repeat them in order to get enough acceleration benefits, they become very area and energy intensive. So this is where analog hardwares come in. But I need to stop here for a second for disambiguation, because in the last few years, there have been so many different analog hardwares that are being talked about. So the question is, which one that I'm meaning here? First of all, we all know that the predecessors of the computers we have today were analog, right? These were signal processes based on continuous variables such as light and electrical signals in order to imitate complex systems. For example, the one that you are seeing in the slide here is a simulator for pharmacokinetics. So it is basically a machine that simulates the motion of a drug in human body. At the time, if you were to try to do that on a digital processor by defining partial differential equations and doing numerical methods, it would never be able to converge. But instead, this analog machine, comprising of capacitive inductive parts with some active elements as well, it was able to give you the results in a much faster manner. But I wrote on top long past with a question mark, because while it's obvious that they were in the past, they're actually having a comeback in the recent years. But nonetheless, they won't be the topic of this talk. I'm also quite sure that you have heard extensively about neuromorphic processes, where these architectures essentially imitate neuroscience, specifically how synapses spike between one another and achieve Hebbian learning with respect to the timing it takes between these pulses arrive. And I chose to write far future, again with a question mark on top, because while it makes great sense to look at human brain and choose it as a model of very efficient intelligence processor, it turns out simply mimicking what happens at the low level, with these spikes and whatnot, is just not enough to obtain enough of a functionality to justify the cost of building these architectures. So a day will most probably come once we understand human brain much better for these architectures to make sense, but they seem to have some work to be done. Instead, the ones that I am going to talk about today are the ones that I choose to call intrinsic processes. You might have seen them as resistive crossbar arrays. And what these machines are, these are efficient linear algebra machines. To describe what they do in a simple sentence, they do local and fully parallel information processing using physical properties instead of Boolean arithmetic. So these are local machines, or also called as in-memory compute type machines, in the sense that the physical location where the weight matrix is stored happens to be the exact same place where the bulk of the operations are executed. So whenever you need to do inner or outer products, you don't need to go to memory and bring the weight matrix to the processor, as it already is the processor. You still need to bring input matrices and write back the outputs, but nonetheless, choosing an option as such drastically reduces the amount of memory communication you have and partially solves von Neumann bottleneck. In addition, these are fully parallel machines, and they can do matrix inner and outer product in ON computational complexity compared to the ON cube I was mentioning for the digital ones. And maybe most importantly, they achieve this parallelism not through complicated and intricate circuitries of transistors and logic gates, quite complex circuitries, but instead simple and single resistive device elements. So you basically replace few hundred transistors in a GPU with this one device unit. And the reason that they can do this replication is they rely on intrinsic computation through device behavior. For example, they do multiplication through Ohm's law, accumulation through Kirchhoff's current law, and possibly more interesting than the both of them, they can also do rank 1 updating for training purposes through certain set of device physics as well as probability or statistics. So if you look closely to one of these machines, this is roughly what you're going to see. You will see a crossbar array of resistive device elements where the weight matrix of the network layer are represented by the conductance values crossbar array. So then if you represent the input vector with the raw voltages, the resulting column currents will simply be the inner product or the dot product between the input vector and the conductance matrix. What is nice about this is if you double the size of this matrix, it is still going to take the exact same amount of time. The currents will still pretty much instantly emerge upon the application of these voltages. So it is constant time for vector matrix multiplication and linear time, or n, for matrix-matrix multiplication. This is nice, but on its own, it's not at all enough. For capturing training applications, one also needs to be able to program all of these conductances in a parallel manner. And the method to do that is admittedly much more complicated with respect to the one I just showed before, but there does indeed exist a method to completely calculate the update matrix and on the existing conductance values in a parallel manner. And this method basically relies on, as I was telling earlier, probability and device behavior. So the probability part is relatively easy to achieve because it is essentially done by the peripheral architecture. So the probability one refers to these generation of these pulse trains that I'm showing at the rows and columns. So that can be easily done. But as you might imagine, the integrity of this operation heavily relies on the unit device behavior. If they act in a certain way, then you can indeed update this matrix in an accurate manner. And if they don't, then it just simply becomes a wrong updating, therefore you cannot train a neural network. So let's have a look at what are those device properties, where the animation kind of betrayed me. But that's okay. So what we are hoping to get from these devices is a gradual change, gradual conductance change. So these devices will have a conductance value, right? We will send a positive voltage pulse to increase the conductivity by an incremental amount. Then we will send another positive voltage pulse to increase it a bit further, so on and so forth. And when we invert the polarity of the voltage pulses to apply a negative one, it should come back again by an incremental amount, another one, so on and so forth. So we want this, and at the end of the day, if you don't apply any pulses, by the way, we want the conductance value to remain exactly where it was last set to. That is why these devices are often called as non-volatile programmable devices, or non-volatile programmable resistors sometimes. What we also want from these devices and also the preferably linear modifications, and definitely symmetric ones. So from symmetry, what I mean is if you do a positive voltage pulse followed by a negative one, what we want to happen is that it should come back to the exact same point.
If there's things here, you use the hand.
Oh, yeah. Working now. Perfect. All right, so as I was saying, what we expect from these devices is gradual change, preferably linear, and most certainly symmetric. That's very important, so I'll repeat it again. So symmetry here refers to if you do an incremental change followed by a decremental change, you want it to go back to the exact same point. So in the last part of this talk, I will explain why that matters so much. But for the time being, we'll just continue with that. So let's have a look at the most mature device technology we have that are designed for this kind of applications, which are phase change memories that are based on reversible phase transitions in chalcogenide glasses. And while you can see in the going upwards, it is at least smooth, but then if you try to reduce the conductance back, it is rather abrupt. So it is absolutely asymmetric, and therefore this property of theirs renders them unsuitable for analog deep learning applications. A leading contender is filamentary RMs that are relying on formation of a narrowly confined conducting path inside of an insulating matrix. And while these devices are also asymmetric, far better than PCM admittedly, but still, their major problem is that they have very low yield and high device-to-device variability. And this is actually an inherent property to them because formation of these filaments are, by their nature, random. So that is most possibly the reason why it has been so difficult for engineers to find a way to have reliable filamentary devices. In contrast to the reliability issues of filamentary devices, magnetic and ferroelectric devices have superior reliability. But so far, it has been proven to be difficult to get more than a few states with these devices, even more than 2 at some point. So when you apply a programming pulse, it just goes from the lowest conductance state to highest conductance state in an uncontrollable manner. And actually, if you stop here and think about for a second, all of these technologies that I'm showing here, and many more that I didn't, were originally designed to be memory devices. They were designed to store information. But in this case, we are working on an information processing application. So learning, by almost its definition, it is to tune the weights, the parameters, to optimum value through a series of many incremental changes, right? So we need to optimize these devices for state transition properties rather than just state preservation. And that is exactly where the field of non-filamentary ionic devices started coming into, where you can think of them at a high level as a semiconducting device where you can control the amount of dopants you have in the channel in a reversible manner during the application. So you can electronically control post-fabrication how many dopants exist in your channel layer. Looking them into more closely, they comprise 3 key layers. There is reservoir at the top, which contains essentially infinite ions, which are going to act as these dopants, and then an electrolyte, which permits the flow of ions upon the application of an electric pulse while completely insulating any electronic flow. And finally, an active layer, the semiconductor layer that I was mentioning before, which is often used as a transition metal oxide, is usually chosen. And this material has a variable conductivity upon insertion and extraction of ions. So depending on the concentration of ions in the active layer, you will determine the conductance state of this device. Actually, when you use lithium as the working ion, what you end up having is essentially a lithium battery, solid-state lithium battery. And thanks to the advancements in lithium materials over the many decades, a lot of successful implementations were done based on lithium. But the fundamental problem is lithium is not a CMOS-compatible material, so we cannot make these devices at the back end of the line to be monolithically integrated at the front-end CMOS circuitry. That's exactly why oxygen-based alternatives were promoted, as at least most oxides are CMOS-compatible. That checks that box, but the problem is oxygen is large, and it's also heavy. So A, it's not going to be all that fast to be moving this large and heavy ion. B, it's not going to be particularly energy efficient. And C, actually, if you move this ion back and forth into the material, it can cause to physical degradation, mechanical degradation of the materials. So naturally, attention finally got into hydrogen-based devices or proton-based devices. But while the theoretical idea behind hydrogen makes perfect sense, the lack of protonic solid-state materials critically limited their integration and scalability, where the early demonstrations were done with liquid electrolytes, for example, or polymeric electrolytes, neither of which necessarily lend themselves all that well to conventional silicon processing. So a key innovation that we have done in our group over the last few years was to invent a silicon-compatible, by means of CMOS materials and BOL processing, solid-state protonic electrolyte. And we achieved that by using phosphosilicate glass, or PSG. This material is essentially amorphous silicon dioxide that is doped with phosphorus. So we can deposit them using conventional methods. And it is actually quite an old material and have been around for a while, so we know quite a bit about them. What is nice about them is, for our purposes, that they're good proton conductors at the same time achieving good electronic insulation properties. And as a separate note to that, they also achieve this without relying on the environmental humidity or absorbed water to conduct the protons, but instead it can intrinsically, its glass structure allows this to do this in an intrinsic fashion. And in the last bullet point, I also wrote that these materials at PSG has a high breakdown field, which is by all means an unconventional metric to cite in an electrolyte material. And to understand why that matters at all, we need to have a look at how proton motion actually happens in these devices. So protons move in these amorphous structures through a series of hopping events, each hopping associated with a certain energy function, similar to the one that I'm showing on the bottom right. And even for PSG, which has a relatively low activation barrier, these barriers have usually quite high energies, in this case 0.4 eV. So at room temperature, where your thermal excitation is only 26 milli eV, it's going to be very difficult to get across these fields and have sufficiently many hopping events to have proton conduction. And actually, at this point, again, this is not going to be of surprise to hear that previous ionic devices, the speed limit for the protonic devices as well as a few others were in the milliseconds. So you could only send millisecond-long pulses in order to push enough of ions into these materials to get an appreciable change. And while it was scientifically interesting, milliseconds is definitely not a time scale to be related with in compute applications. So this situation changes drastically if you can afford to apply an electric field so powerful enough to tilt the energy diagram to the point of extincting the entire barrier. So it essentially becomes barrier-free motion or ballistic motion. But as you can see in this, from this plot, the field that we're talking about is 10 megavolts per centimeters or volt per nanometer. So these are very high electric fields, and many electrolytic materials would just simply turn into ash if you were to try these. But instead, the intrinsic properties of PSG turns out to be able to have these amount of fields in fast pulses and work through many cycles without going through any degradation. So when we built these devices at the nanoscale at 30 nanometer node, to be specific, we also saw state-of-the-art combined properties for any programmable resistor device technology for, again, analog deep learning purposes. Well, first of all, these devices now are very, very fast. We were able to operate these devices by using 5 nanosecond pulses. To put that again into context, they are a million times faster than the previous state-of-the-art, which was operating in milliseconds. And not only that, each pulse actually carries a very little amount of energy. So each pulse, in this case, carries 2.5 femtojoules, which of almost all of it is CV squared. So it is the capacitive charging-discharging losses we have. And if you actually try to look at what is the energy associated with moving the protons themselves, it is only a mere 15 attojoules. So on top of those nice two top metrics, you also see that the modulation behavior of these devices in the middle figure is near ideal in the sense that it is nicely linear and very nicely symmetric, and it covers a 20-fold conductance range through 1,000 distinct pulses. Continuing on that, we also saw devices that show good retention and endurance metrics, and in a very recent study, we also analyzed how fast they actually respond immediately after the pulse, right? Because you can send a pulse and maybe the change occurs at an elongated equilibration period. So we needed to check that. And as far as we can see here with a 170 megahertz signal, the transition from one state to another upon the application of a 5 nanosecond pulse, which you can see on the right figure, which is an inset from the one in the left, it is pretty much instant, or technically speaking, sub-microsecond to say the least. So it is my great pleasure to share that since we made these results public in around last month, we actually had quite a lot of interest from academia and industry, and we are now moving fast toward building larger systems with these devices. But while this slide concludes the device portion of this talk, the task is far from done, right? We have unit devices, they need to be arrayed, then the periphery needs to come in, and then you need to run algorithms on them. So while for the sake of time, I won't talk about architectures today, so the periphery and peripheral structures that are needed, I will still look at the algorithms part for analog deep learning. So at the end of the day, what we want to do is to train a neural network, right? So therefore, we need to make sure the changes that we exert on these devices accurately capture the training operation that we want to do, right? And for a very long time, people said, okay, once the devices are ready, we will simply use the algorithms that are designed for digital architectures. For example, stochastic gradient descent, that has served us so well in the digital architecture. We have a lot of varieties of it as well. And it was a very reasonable idea, but it turns out that since analog architectures have non-idealities in circuit and device level that simply does not exist for digital architectures, we need to come up with new algorithms that can tolerate some of these non-idealities such that we don't compromise the act. And the way to test these suggestions, like for example, what is going to be the effect of a certain non-ideality on the training performance of a neural network, we still rely on simulations, given that we don't have that big of a system. So what we do is we simulate the device behavior and the circuit behavior in a training example. For example, training a convolutional neural network, training a LSTM type network, fully connected network, and then seeing if there is any degradation compared to a digital baseline. That's how we assess if any of the non-idealities matter, like how much. So here I'm showing one of those simulated examples. This is a LSTM type network trained with stochastic gradient descent, the traditional algorithm we have and love, based on 3 different device models of increasing levels of asymmetry. And again, for those who are not familiar with LSTM, the task of this network is to guess the next character in a string. So you can think of it as an autocomplete. Although it works quite differently, that is what it's trying to do. And in this plot, going upwards means that it is doing it worse. So this is the error function, which is usually used as a cross entropy. It's a logarithmic function. And higher the curve means that you have a worse network, essentially. And what we are seeing here is that with respect to this black baseline, or for perfectly symmetric devices, all of the asymmetric devices have a very significant loss of accuracy. And it's actually interesting to see that even the blue one has that, because to the naked eye, it looks pretty symmetric. But that is actually showing us how fundamental of a problem that we are dealing with here. And since actually most of the devices out there belong to green and red families, this problem has been seen a lot by a lot of people. In literature, this was probably one of the biggest problems of analog deep learning for, again, learning, training applications. So people have seen it, and therefore people also came up with some proposed solutions to mitigate the negative effects of asymmetry. But all of those solutions, proposed solutions, fall into one of the 2 categories, and in some rare cases under both. Some of them suggest that we actually employ a feedback loop. So we do an update, then check it, and if it's not right, we should compensate for it. But as you can see from how I described it, this is a serial operation. So you need to go look at all of them and then do it one by one. So it sacrifices parallelism. And at the end of the day, yes, maybe you are fixing the effects of asymmetry with this method, but you also don't have an accelerator anymore. You maybe have a decelerator. So it kind of starts beating the purpose. And the second school of thought suggests that maybe we can put a compliance circuitry around each device and force it to act in a certain way that we want to, right? But this clearly contradicts with what I said in an earlier slide for GPUs, each core having hundreds of transistors. So if we now start putting just transistor circuits to force this device to act in a certain way, we are essentially sacrificing area and energy efficiency benefits altogether as well. So maybe what is the most interesting about this picture is while it was a widely seen problem empirically, everyone were aware of it, that was happening in all simulations, no one exactly knew why. What was the theoretical underpinning of the asymmetry being such a big problem? We understood noise, why noise was a big problem. We understood how big of a problem it was. We understood saturation. We understood many other non-idealities. But asymmetry was an alien one when we really couldn't understand what's so wrong about it. So to explain that, I will use this example, which is probably the simplest learning case possible, single parameter regression. We are just going to train one parameter. And what we're going to do is that we have this data set, x's and y's. They have a mean, which is the green line, g naught. And they have some standard deviation, epsilon. And what we will try to do is to find the average of this data set. Not a particularly exciting task, but it is going to show us something interesting. So if we try to do this, with SGD, the network we all know, and use a perfectly symmetric device, as the one that I'm showing here, nothing particularly exciting will happen. We will start from an arbitrary point, we will start the training. As training goes on, we will slowly converge to the optimum value, G0, which is the mean of the data set, the one that we are looking for, and then it's going to converge there and stay there, what we expect from it. And maybe one thing to note here is that even when we see it as if it's flat converged, it's actually moving in its vicinity. So it's not statically staying there, and that will become important. Instead, because some of the values in the data set will be above the mean, some of them will be below the mean. If it's above, it's going to be go a little bit up. If it's low, if it's going to go a bit down. On average, they will cancel each other out. That's the definition of mean. But other than that, it's just going to be in the vicinity, at a narrowly tight band around this optimum value. And that's why we should call this value as a dynamic equilibrium. It's not a static equilibrium, it's a dynamic equilibrium from the data sets and algorithms point of view. So let's now look at what happens with an asymmetric device. So as I defined symmetry early on, the definition of symmetry is if you do an increment followed by a decrement. It doesn't need to be immediately followed, but at any time, they should cancel each other out. But here, if you are, for example, above this orange line in the middle, if you do one increment, one decrement, since the increments are saturating and decrements are sharp, you pick up a net negative term. And if you are below the orange line, vice versa. So what's actually happening is, wherever you are in this device, whenever you update it, it actually has a component that shows towards this orange point. This orange point, of course, has a significance because it is the only point in this graph that the incremental changes are in magnitude equal to the decremental changes. So that's the only point that if you do increment, decrement, increment, decrement, it will be able to stay in that. So for that reason, we can call G-symmetry, first of all, we can call this value as conductance as G-symmetry or the symmetry point. But it is also the dynamic equilibrium from device's point of view, because that is where a device wants to sit at. If you want to modulate this device a lot, this is where the device will want to go to. So it is its own stable point. So when you try to train stochastic gradient descent on top of this device, what's going to happen is the convergence will fail. Instead of converging to the optimum value we want, the green line, that is representative of the data set's value, it's going to converge in somewhere in between the optimum value and the symmetry point. Because what's happening here is, as you are further away from the optimum point, the algorithm generates updates such that to bring them close to the optimum point, which is represented by the magnitude or the length of these arrows. And when you start getting away from the G-symmetry, each update you start having will actually start drawing you even more towards the symmetry point. Because as you can see from the top here, if you do an increment, nothing happens. If you do a decrement, big change happens towards the G-symmetry. So instead of going to the optimum value, you will end up being somewhere in between them. And this is coming from, as I said, due to the competing nature of the two equilibria. And here is a quick thought experiment. Let's say you had a very lucky guess. You actually started from the optimum. It happened, right? So if that happens, what is going to happen? We know it from the top graph. You will have net zero random updates, right? Because you're already on the mean. Some of them are above you, some of them are below you, net zero. And we know from this graph, if you do have net zero, you will actually come close to G-symmetry. So even if you start from the unknown optimum point, you will still end up being here. And if you can't even remain at the point that you want to reach, there is obviously no way that you can train this device to get to that network point either. And to put this same understanding in different words, what stochastic gradient descent is trying to do is it knows this energy function that is associated with the error, and it tries to minimize it. That's trying to do in digital, in analog, in anywhere. And we can imagine this as a potential energy, right? It is a parabolic function, for example, and it wants to be in the bottom. But what's happening is, what it doesn't know is, whenever it interacts with the device, there is actually another energy term. Whenever this device is touched, actually it picks another term to the energy function, which is, since it relates to the motion, I chose to write it as a kinetic energy, because it only appears when you modulate the device. If it's standing still, it's not there. If it moves, you will start picking it up. And at the end of the day, it converges to the wrong optimum. It still does converge to an optimum. You saw it. It did converge. It's not divergent. But it is not the point that we are looking for. So to solve that, we developed a new algorithm by separating the competing equilibria two subsystems, where you can have one system that is minimizing the kinetic energy, we call this the auxiliary system, that's only helping us, such that our main system, our core system, can efficiently minimize the potential energy of the system, the one that we care about. And since it optimizes the potential and kinetic energy together, we chose to call this algorithm as stochastic Hamiltonian descent because it minimizes the total energy. And going through the details of how algorithm works is not, I think it's not the best idea to finish how this talk goes, but I will show you it in action. So if you revisit the LSTM example we had earlier, if you train the exact same parameters for stochastic Hamiltonian descent, you will instantly see that the asymmetry penalty that we are doing is now diminished. And what is extremely important about this algorithm is it does not introduce any serial elements or it does not rely on any additional circuitry. So you are basically doing the same operation with the same parallelism, so you don't compromise any of them, and you are still able to now get rid of the accuracy penalty that you had before. But it doesn't end there. There is actually something very interesting. If you try to train the same network using the new algorithm, SHD, on the devices that I showed earlier, the protonic devices, it ends up beating stochastic gradient descent with these theoretical, hypothetical, ideal devices. And this is actually extremely interesting because analog architectures have always been proposed for speed and power benefits, but never ever for accuracy benefits. It was actually something that they had been infamously worse at, and we would only tolerate it in order to get more. But what this result suggests is when the rest of the conditions are also improved, such as the noise and saturation and so on and so forth, some peripheral engineering, stochastic Hamiltonian descent with analog architectures can actually have faster convergence than that of SGD on digital ones and might even have better generalization performance, which is extremely important for AI applications. And I just want to put a note here that there are actually even more applications for analog intrinsic hardware, these crossbar architectures. Specifically, it can be used in generalized machine learning where matrix operations are abundant, and they can also be widely used in randomized numerical algorithms, which I would be happy to talk about as a follow-up to this talk. So the final question that we need to answer then is, how do we innovate faster? Because we still don't have these architectures. We are close, but the progress we want it to be faster. And the idea is we need to abandon this linear progression. We can't just rely on making devices first, then putting them in an architecture, and then run an algorithm, because there are so much that we don't know when we bring them together. What we need to do instead is to co-optimize all of them together as a single entity, such that we can understand what a device non-ideality does on the algorithm level. Maybe we can solve it there, or maybe an algorithm can use a feature of the device. So in order to do that, we will need to rethink this entire structure in a cyclical fashion. We need optimal devices, we will need efficient architectures, and we will definitely need novel algorithms specifically designed for analog. And this is not going to be easy, I'm not trying to say that. It's going to involve all the disciplines from applied physics to applied mathematics and pretty much all of the engineering disciplines that lie between them. But given the potential benefits are so high, the urgency is there, and the progress is also extremely promising, it's possibly one of the easiest actually fields to justify to be working in. So it has been a pleasure of mine to give this talk to you today, and I'd like to thank MIT AI Hardware Program and MTL Seminar Series for arranging this talk. I would also like to thank my professor, Jesus Delalamo, who led this effort, and our research sponsor, MIT IBM Watson AI Lab, and I would be happy to take any questions.
Thank you, Murat. I think we've lost one microphone, so I'm going to ask you to repeat the questions.
Yeah.
So that they get recorded.
Of course, yeah.
Wait, please.
So I think it was maybe slide 20 or so, where you were describing, the stochastic Hamiltonian descent. Yeah.
This one or this one?
The next one, yeah. Yeah. Do you have to know the shape of the asymmetry?
No.
So it still works even if you don't
Yes.
know it?
Yeah.
Is there an insight into
Yeah,
how
so
that happens?
the only thing that you need to know, and even now there are actually newer versions of SHD. But even in this version, the only thing that you need to know is there does exist a point where the G symmetry is valid. So if you, for example, start with a PCM where there is no G symmetry, right? Where you go up, it's nice, you drop, it's done, and one and done almost. For that, it doesn't work. But for any other device behavior, any one of those, whether it's linear, non-linear, doesn't really matter, much more asymmetric than that, it still works with all of them. The only thing that it relies on is the existing shape, not the function. If there are multiple, that's also okay. There just needs to be one. So the only device that I know that it exists and this doesn't work for are PCMs. For everything else, it should work.
One question. I was wondering if you could comment more on the device's scaling abilities. You said it's CV squared limited for energy.
Yeah.
So I imagine there's some carrier transport time.
Yeah.
How does that scale if you move the device? Or?
Yeah. So just to repeat the question is on the scaling directions for the energy, for the performance in general. So what we do see initially is that we try to make these more thin film devices because at some point the thickness of the electrolyte material determines how much operating voltage that you need to apply. So for example, if you have it's about a volt per nanometer, so it's not too bad, but it definitely needs some improvements on top of that. As for the size W and L. Of course, the smaller that you make the devices, you will have less capacitance, right? That is going to help you with the delays and whatnot, and the pulse deteriorates, so on. So far we have made the smallest that ones we made were around 30 nanometers. It doesn't mean that they can't be scaled any further, but from an application point of view, also it's relevant to think. How much area that these are going to consume, right? And these are back-end down-the-line technologies, so they're not as strict. We don't need 2 nanometer node for these devices. We really don't, which is a good thing. But when you actually build an array, bulk of the area consumption is actually the periphery. The ADCs that you need to employ and the memory that you need to put still on chip. So energy is already good, 2 femtojoules. Probably it's going to go far down. The programming voltage will go down as the thickness is reduced, and also when the interface is optimized, you can actually reduce the barrier heights through that. So that's going to go down that way. And as for the application, as I said, the area of the entire chip is simply limited by the ADC. So you can pretty much neglect how much area that these cost, because there is no selector device next to them. There is no any additional circuitry. They just stand alone, and in a crossbar array, you just put them side by side. Since they don't consume too much energy, you don't need to separate them too much either. So there are quite a lot of benefits that come with all of those.
Could you describe the technology you use to deposit or grow the PSG?
Sure. Yeah.
Properties of it?
Yeah. The way we deposit PSG is PECVD. And particularly, we are looking for a nanoporous material. In order to get that, I deposit these materials at a low temperature, actually. The ones that you saw in these slides are deposited 100 Celsius, which is quite abnormally low, I would say, for PECVD. To be fair, if I could go lower, if they allowed me, I would have gone lower. Because the idea is that we don't want a dense material. We rely on surface conduction quite a bit, and we want these pores to be existent. We still don't want it to be too much such that it starts leaking electrons, obviously, particularly at the fields that I'm talking about. But the other critical parameter is the concentration of phosphorus. It very critically depends on how much phosphorus exists in there, which some of it is a mystery, some of it is understood, but it does indeed have a very particular amount of phosphorus concentration. It needs to have the peak amount of proton conductivity while still maintaining good electronic insulation properties.
Still time for more questions? Yes.
A couple of quick questions. One is, it seems as though you're doing everything in one layer, or are you planning on doing it in multiple layers?
There are multiple layers.
There are multiple layers.
Yeah. They're actually, they're obviously not the same, but, oops, let me go back. So you can see from the TEM here, so this is on the bottom there is the channel material, this is the electrolyte, this is the gate, and then the contacts, of course, go even further upwards.
It repeats.
Yes.
The other question is, just as an idea, is there a reason that you're not doing something like having let's say, an 8-bit digital piece over there, which generates a digital analog representation, which can then that particular part can be used to do the computation. I mean, updating it will be, the feedback will be difficult.
Yeah.
As a one-way process.
I think for inference you can do what you just said, and I think there are some people actually try to do that, and then you can actually quite reduce the requirements for the unit device as well, since it mostly relies on the digital. But as you also said, for training it becomes quite chaotic, because I think the inference part of these analog crossbar architectures, actually they were originally suggested in 1950s, so it's an ancient idea. What is new about them is that to update them all in parallel as well. That's why they started becoming of relevance again, and that method relies on analog devices not relying on any feedback loop per se. So for training it would be a bit tricky, but for inference, absolutely. But also, to be fair, for inference, there are so many things that you can do, I would say. Like, for example, you can prune the network first and then reduce the bit requirements to just 2 bits. And then it is already consuming so little, it becomes very difficult to actually beat it at that point. Whereas for training, they cannot afford it, right? You have to have at least mixed, more than 8 bits for sure, and even that 8 bits is not real 8 bits, it's mixed 8 bits, it's hybrid. So for training, they become of much more relevance, and plus it's a bigger application too. And yeah.
One more question?
Just one more, actually.
Yeah.
Is there a way this can be used for one very obvious purpose, which is things like cryptocurrency, data mining, and things like that?
It can be.
Repeat the question.
The question was, can it be used for crypto mining, specifically to a cryptocurrency, or in cryptography in general, I guess. It can be. I mean, basically wherever you have high intensity matrix operations, linear algebra operations, these can be used at. If it is more towards just matrix multiplication, they are less valuable with respect to if they rely on rank 1 updates. So if you have an application where you need to parallelly program them, such as matrix sketching, matrix streaming, and some randomized numerical algorithms such as quasi-Newton, for example, then they become very valuable. So that is the direction they can go to, and they are basically generalized machine learning fields. For cryptography, they can be used as a MATREC engine. Again, the question is this the MATREC engine that you want? Maybe. Because it makes sense. But the rest of the requirements, if you actually look at it as a whole system, it remains to be studied a bit more detailedly.
All right, we're going to stop at this point. Murat, fantastic talk.
Thank you.
I'm very proud that you have inaugurated this new joint seminar series between MTL and the AI Hardware program. I cannot think of any better way to kick this off. Thank you, fantastic.
Thank you very much. Thank you. Thank you.